Amortized complexity. Okay, so amortized complexity is the average time taken over a sequence of consecutive operations. Um, okay, so in average worst or best case complexities, we're concerned with the performance of one independent operation, whereas with amortized complexity, we want to think about the average time complexity over a number of successive operations. So we want to look at the bigger picture in a way. So let's look at an example. Hopefully that should clear up. So the time complexity of linear search, where the search value is stored in X, assume that the length of the array is N. Successive, yeah. So worst case, X is at the end of the array. Best case, X is at the beginning of the array. And our average case is if X is in the array, where X is... We consider the likelihood of X being on any position as uniform. In other words, the chance that X is on position 0 is the same as for 1 or any other operation. And so the average number of traversed elements is equal to, we traverse 1 if it's in position 1, or we traverse 2 if it's in position 2, or 3, or n if it's in the very last slot, all divided by n. And with a bit of algebraic manipulation, we can get this fraction here, which is just n plus 1 over 2. So the average case for linear search is n plus 1 over 2. Okay. The average number of traversed elements is 1 times p1, so this is the likelihood or probability that that happens. Assuming that all of it's uniform, these would all just be equal. Yeah, so in the uniform case, pi equals 1 over n for every position. This is just average case, but if we want to look at amortized costs, so say oil consumption is 8 litres per 100 miles. Price of 1 litre is £1.20 and £9.60 per 100 miles. So that just translates to that. We just times that by 8. Okay, so extra expenses, new tyres, £320 every 70,000 miles. New brakes, £250 every 30,000 miles. Fixed gearbox, £300 every 130,000 miles. And fixed clutch, £406 every 100,000 miles. So this is an extra £1.93 per 100 miles. And so we've worked out the amortized costs. So we don't care about a single operation. We care about, in the long term, if we do a bunch of operations, what's the amortized cost? And so how this has been worked out is... Actually, let me make a new page. Okay, so the price of 1 litre is £1.20. This is the price per 100 miles. So £9.60, this is for oil. And then we look at these extra expenses. So for example, new tyres, 320 for 70,000 miles. If we want to get however much it is for 100 miles, we're going to want to divide that by 700. So this is tyres. If we want to look at brakes, 250 every 30,000 miles. Every 100 miles, that's that divided by 300. So this is going to be our brakes cost. Looking at the gearbox, this is 130,000 miles. To get 100 miles, we want to divide that by 1,300. So this is the gearbox. And then the clutch, 406 divided by 1,000 to get however much it is every 100 miles. So this is the clutch. Round up or round down. I'd probably just leave it like this, work out the result, and then when we get the result, we just round it to whatever it's closest to. So if we add these up, we get £9.60 plus... Okay. So if we run that calculation, we add them all up, we get 11.527. So 11.527 whatever. And we've rounded this to 11.53 to get the amortized cost per 100 miles. So that's how we'd work out the amortized cost. So we look at different things. We look at a sequence of consecutive operations. In this case, we're looking at, for example, the average. If we split these costs between 100 miles, or if we're looking at 100 miles of this 70,000 miles or of this 30,000 miles, and then adding that up, this is the extra cost per 100 miles for all of these extra expenses. And then we add that onto the £9.60, and this gets our amortized cost. So let's say we want to work out the amortized complexity of this dynamic array sort of implementation. So say we initially allocate an array of 1,000 entries, and whenever the array becomes full, we increase the size by 100. So to insert n entries, starting from empty, how long does it take? Let's assume that n is 1,000 plus 100 times some integer k. So if k is 0, let's just say n, we're inserting 1,000 things. If k is any integer greater than 0, it's going to be 1,000 plus 100 times that integer. Okay, so in total, the number of insertions is 1,000 plus 100k, because we're going to insert every element. And the total number of copies is 1,000k plus 100 times 1 plus 2 plus blah 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 plus k minus 1. The reason we've done that, so the idea of this formula is if k is 0, for example, that means we don't have to grow the array anytime. So k is the number of times we grow the array. So if we have to grow the array 0 times, we don't have to copy anything. So we just insert 1,000 values, and assuming k is 0, we don't insert anything else. And our copies will just evaluate to 1,000 times 0 plus 100 times 1 plus 2 plus, but this would just go up to minus 1, essentially. Wait. This would... I mean, I'm guessing they're assuming that k is not equal to 0 in this case, but when they've simplified it down, we've kind of taken that assumption on board and said k is not equal to 0, because if we times this out and then 1... Wait, let me just try and... So yeah, so this bottom part, depending on whatever our k value is, if k is 0, this just evaluates to 1,000 times 0 plus 50 times 0 times minus 1. This is all just 0, which just means if k is 0, if we've not had to expand the array, we're not going to make any copies. It's just going to be this case here. If k is 1, then we're going to have to expand the array once. So we're going to have to copy these 1,000 values up. And so that's why we have, this is accounting for this scenario here, if k is equal to 1. If k is equal to 2, we have to do this. And subbing k as 2 into here, we'd get 2,000 plus 50 times 2 times 1, which gets us 2,100. And in total, we've done 1,000 plus 1,100 copies, so that's 2,100 copies. And so we can calculate the total number of insertions, and we can calculate the total number of copies. So if we want to work out the amortized cost of an insertion, how many insertions are we doing in total? We're doing 1,000 plus 100k insertions in total. And for every insertion, we have to do this many copies. So this many operations in terms of copying. 1,000k plus 50k times k minus 1 copies plus 1,000 plus 100k insertions. So in total, we're doing this many actions. So 1,000k plus 50k times k minus 1 plus 1,000 plus 100k. So this is how many actions we're doing in total, where this part is just this the number of copies, and this part, oops, and this part is the number of insertions. Okay, so we've got these calculations. Now what we can do is we can divide this by the total number of insertions, which is just this number up here. So 1,000 plus 100k. And if we work this out, let's see what we get. Okay, so 1,000k plus 50k squared minus 50k plus 1,000 plus 100k. Okay, so that's 50k squared plus 950 plus 1050k. Is that plus 1000 over 1000 plus 100k. Okay, let's see. I don't wanna get into. So, right. Okay, so they didn't actually simplify it down, but the idea is because the numerator's theta of k squared and the denominator's theta of k, the whole fraction is in theta of k, and so we can also say this whole function is O of n or O of k, and k is linear to n because we can represent it with this linear relationship, n equals 1000 plus 100k, and so the amortized complexity of insertion would just be O of n. So we've taken the total number of actions per insertion and we've divided it by the total number of insertions to get our amortized complexity of insertion. Yeah. Okay, in terms of Java's array list, let's just go through this example as well. So Java array lists initially allocates an array of, say, 1000 entries, and whenever the array becomes full, instead of increasing the size by 100, we double the size. So to insert n entries, starting from an empty array, how long does it take? So let's assume that the number of entries we're doing is 1000 times 2 to the power of k for some value of k. If k is 0, we're just not increasing the array size. If k is 1, we're doubling it. If k is 2, we're going to double it twice. And so that's what this k value is representing here. In total, the number of insertions is 1000 plus 1000 times 1 plus 2 plus 4 plus all the way up to k minus 1. So if k is 0, we're just going to insert 1000 things and then we're going to stop there. If k is 1, we're going to insert 1000 and then we're going to insert another 1000 because it's going to be 1000 times 1. If k is 2, we'll insert 1000, then 1000 times 1, then 1000 times 2. And we'll keep doing this up to 2 to the power of k minus 1. And note that this isn't 1, 2, 3, this is doubling every time, just because we're doubling the size of the array, we're not increasing it linearly. And in terms of the number of copies, it's the same formula, just without that 1000. So in the first case, we copy 1000 things up. In the second case, we copy 2000 things up, and so on and so on. I believe this whole thing can be simplified down to 2 to the power of k, all just minus 1, and this can also be 2 to the power of k minus 1. Yeah, okay, so to work out the amortized cost of one insertion, let's just trace through what this would actually mean. Okay, so number of insertions is 2 to the power of, or 1000 plus 1000 times 2 to the power of k minus 1, and this is just 1000 times 2 to the power of k minus 1. Okay, so in total actions equals 1000 plus 1000 times 2 to the power of k minus 1 plus, and then that bottom part, the number of copies, is also actions we need to consider. So this is our total number of actions, and then our total number of insertions is just what we've been given, so 1000 plus 1000 times 2 to the power of k minus 1. And then to work out the average cost per insertion, we do the total actions divided by the total insertions. So 1000 plus 1000 times 2 to the power of k minus 1 plus 1000 times 2 to the power of k minus 1, all over 1000 plus 1000 times 2 to the k minus 1. So we have this. Now to work this out, I'm going to factorize it out like this. So I'm going to expand it all out. So 1000 times 2 to the k minus 1000 plus 1000 times 2 to the k minus 1000 over 1000 plus 1000 times 2 to the k minus 1000, and that just becomes this minus 1000 over, okay, I believe we get this, and we can split that up into 2 minus 1000 over 1000 over 2 to the k, which is just 2 minus 1 over 2 to the k. Have I done anything wrong there? Let me know if I've done any illegal moves there. But I believe that's just 2 minus 2 to the minus k. Okay, so we're left with this cost per insertion. Hopefully that's similar to what we've got here. No, okay. Wait, so k, we know n is 1000 times 2 to the k. N equals 1000 times 2 to the k. So we can say the relationship between n and k is that k equals, or n over 1000 equals 2 to the k, so log base 2 of n over 1000 equals k. So k is in O of log of n. So the 2 to the minus k is negligible in effect, because the headline of this is actually this part here, it's not this part here. So we'd take our time complexity, insertion cost would actually be in O of 1, just because O of if we took this just means that it's decreasing as we increase the input size. So constant is worse than this, so this is our headline, big O. Does that make sense?